Lesson 3, the heart of the unit. We're going to take our time on this first example, so let's get into it. The first thing you will notice that this here, these words, say that this is a graph of f prime. Oh, I cannot emphasize this enough. This is not a graph of f. This is a graph of f prime. And what does f prime mean to us? Of course we know this. F prime means slope. So let's digest this. The graph that we're looking at is not the graph of the function f. It is a graph that gives us the slope at varying points. So as an example, you see this point here, 2, 2. That means that at 2, the slope of the function that we can't see the graph of f, we can only look at the slopes. So the slope at 2 is 2. Over here, it tells us, and we'll take a look at this, that this is a semicircle. So this tells us that f prime of -4 is equal to 1. That's what these points on this graph tell us. If you are tempted to say that the slope at that point is 0, what you're assuming is that you're looking at a graph of y equals f of x. We're not. We can't see this graph. So calling this a horizontal tangent is not the appropriate language for this graph. I just want to say it again, that at this point, because the y value is 1, that means the slope at 4 is 1, because this is a graph of slopes. So let's just read it now. Let f be a function defined on the interval -5 to 5 with, and here's our given information, f of -1 is equal to 3. We cannot see the graph, so we don't know this information unless it's given. F of -1 equals 3. On some graph that I can't see, at -1, the height is 3. The graph of f prime, the derivative of f, or the slope of f, consisting, now tells us we have 2 semicircles and 2 line segments, is what is shown, in this case, to the left and in your notes above. For emphasis, I'm going to rewrite that information. F of -1 is equal to 3. That's given, and that's the only way we know that property. Okay, before we go parts A through F, I do want to point out one other thing. A function is positive when it's above the x-axis. So what I'm going to do right now is I'm going to highlight positive in this yellow color. So positive just means above the x-axis. So where I have yellow, this function that I see is positive. And then a function negative means it's below the x-axis. So I'm going to highlight in this blue what it means to be negative. The function is negative below the x-axis. It's important again that this function is a function of slopes. So where I have highlighted yellow, it means the slope is positive. And when I have highlighted in blue, it means the slope is negative. And now we're going to pull this all together to answer some questions using the spirit or heart of derivatives to answer the questions. Part A asks us to find f prime at 3. Literally, that's only asking us to find a point on this slope graph. So at 3, I want to figure out what the y value is. Not what the slope of this segment is, but what the y value is, because this graph tells us slopes. And this is equal to 1. We do know that's a line segment. I'm not just guessing. I can see clearly here that the slope goes down 2, so down 2 over 2, so I see the slope of this segment is -1. So if I go down 1 over 1, that tells me that the y value is in fact 1. So 3, 1 is the ordered pair, or in other words, f prime at 3 equals 1. That is a point on the slope graph. Point on slope graph. Cool. for question part B. For what x values is the function f decreasing? F is decreasing. And see, what's beautiful about this is I can't see the function f. So I can't just visualize like a fourth grader would, where is the function getting smaller? I can't visualize that. So f is decreasing on, and then I have to put an answer for what values of x the function is decreasing. But I remember from earlier in the unit the reason for it. And the reason is because the slope of f is negative. Remember that? So we can see where the slope is negative. I see the slope is negative where I have the blue highlight, because that's where the slope graph is below the x-axis. So f is decreasing on, and I'll use the standard bracket notation, -3 to 1 in union with 4 to 5. Because the slope of f is negative on -3 to 1 in union with 4 to 5. I hope you see that that is the heart of this. Below the x-axis means negative, and so I am finding the x values where the slope is negative. In part C, we want to know where the function f that we cannot see, we want to know where that function has a relative max. F has a relative max at, now I'm going to find an answer or answers where that is true, and then I'm going to write the reasoning. So this reasoning should be sort of conditioned into us at this point, and it's because at these, now if it's the, I'll change it later, but at these x values, f is continuous, and then here's the key feature regarding slope. The key feature is the slope of f, you remember this, goes from positive to negative. The slope goes from positive to negative. So that means where I go from yellow to blue. So let's find that. Hopefully, can you do this now before I get to it? Right here. Boy, that certainly doesn't feel like a maximum because it's a zero of the slope graph. In fact, I'm telling you something important here. At this point, the slope is 0 because the y value is 0. But because it was yellow before that and then blue after that, the slope goes from positive to negative at x equals -3. Do you see another place, another x value where we have a local or relative max? Hopefully you're saying at 4. Because the slope goes from positive to negative at 4. Super cool. The ability to analyze a function that you cannot see using a derivative or slope graph is at the heart of what the College Board is testing on the AP exam in regards to derivatives. Part D wants to know where the graph of f that we cannot see is concave upward. F is concave up on. Okay, so concave up on, I don't know. And before, when we had linear segments, we said there was no concavity, but that was true when I was looking at a graph of f, but now I'm looking at a graph of slope, so that's not the case. F is concave up on, we'll leave that blank, and we'll fill in the reasoning. The reasoning is because the slope of f is increasing. Remember, that was our reasoning for concave up. The slope of f is increasing on, and then we'll choose some interval. All right, so we need to do this. We need to see where the slope is getting bigger, where the derivative is getting bigger. See, now I am looking for a function getting bigger. So on this portion, the function was increasing. On this portion, the function's increasing. And again here. Those are the parts where the slope is getting bigger. So concave up on -5 to -4 in union with -1 to 1 in union with 1 to 2, and because the slope of f is increasing on this interval. Part E says write an equation for the line tangent to the graph of f that we can't see at x equals -1. So if I resort to the knowledge I have on this, y minus f at -1, or the format maybe I should say, is equal to f prime at -1, that's our slope, x minus a -1, so x plus 1, point slope form. So I'll need f of -1, and I'll also need f prime at -1. If I come over to the graph at -1, this is a semicircle, and so this point here, since the radius is 2, this point here has a y value of -2. So where does that go? Does that go with f of -1 is -2, or does that go with f prime of -1 equals -2? Well, since this is the slope graph, that goes with this one. So now I need f of -1, and the only way that I know that information was because it was given. And that's why it was given. Cool. So I'm going to plug that in. Y minus 3 equals -2 times the quantity x plus 1. Point slope form. Before we move on to f, I do want to point out, I'm not sure I mentioned this, but in part C, do you notice that it said for what values of x from -5 to 5? So what they've essentially done was ruled out any endpoints, so you didn't have to worry about if there was a maximum or a minimum at the endpoints, because it said what are the relative maxes inside -5 to 5, not including. At any rate, let's do part F. And part F is not even calculus. It's asking us to write a piecewise equation for the graph that we see. And this is more of an algebra review. Let's do maybe the line segments first. I'm going to write them each individually, and then we'll piece them together. So this line segment here, if I use point slope form, I can say y minus 0 equals the slope. Okay, so the slope is rise 2, run 1, so the slope is 2, and then x minus 1. I'm using this point here, which is the point 1, 0, and then we see that reflected. So that would be y equals 2 times the quantity x minus 1 for that particular line segment. This other line segment here, I'll also use point slope form. I'll use this particular point, y minus 2 equals m. I need the slope, which we already talked about, the slope being -1, times the quantity x minus 2. I do want to solve for y here because I'm going to write it as a function. So we have 2 minus the quantity x minus 2 for the other linear portion. Let's move on next to the semicircle. I'll pick this semicircle first. And you will notice that the center of the semicircle is at -4, 0. So how does that get reflected? Well, x minus a -4 becomes x plus 4. And that's going to be squared. That's the standard form of a circle. Plus y minus, well, since the center is at 0, y minus 0 squared equals the radius squared. And the radius is equal to 1, and 1 squared is 1. Okay, so if I solve this now, I get y squared equals 1 minus the quantity x plus 4 squared. If I solve for y, I get y equals plus or minus the square root of 1 minus quantity x plus 4 quantity squared. But plus or minus would give us a complete circle. I don't want the complete circle. I want the semicircle, or half of the circle. And since I have the upper half of the circle, I need the plus version of it. So this burgundy semicircle has the equation y equals positive square root 1 minus quantity x plus 4 squared. We're going to do the last one now. We're going to find the equation of this semicircle here. The center of that semicircle is -1, 0. So I have x plus 1 squared plus y squared equals radius, which is 2. 2 squared is 4. Y squared equals 4 minus x plus 1 quantity squared. Y equals plus or minus the square root 4 minus x plus 1 squared. Since I need the lower half of the semicircle, it's going to be the negative radical. And so I will write that, oh geez, where will I write that? Here. Y equals negative square root 4 minus x plus 1 squared, all under the radical. So I am ready to write the original question, which is an equation for f prime of x in a piecewise format. So f prime of x equals, it's going to be a piecewise equation. I'll start left to right. It was square root of 1 minus quantity squared. And the condition for that was when x is between -5 and -3. Then we had the other semicircle, which was negative square root of 4 minus quantity squared under the radical. And that was when 3 is less than x, which is less than or equal to 1. Finally, we had the pink line segment. So 2 times quantity x minus 1, and that's going to be for 1 less than x less than or equal to 2. And our last piece line segment, 2 minus the quantity x minus 2, and that's from 2 less than x less than or equal to 5. You may have noticed that I used equals on the top part with the -3, and then the -3 in the second part of the piecewise equation, I used the form without the equals. That's because I have to choose an equal to be part of one or the other here. I could have put the equal with the second part and left it not equal with the first part, but the function will have a unique property at each x value. So where they intersect, it will either belong to the burgundy semicircle or the blue semicircle. Just pick one.